right, so we have looked at some derivative properties by examining familiar basic functions, but there are a few more to do. Let's just review what we have so far. I'll call this first one the constant property, that if my function is just a constant function, just a number, then the derivative is 0. And we motivated that by noticing that the constant function is a horizontal straight line which has slope 0. And the derivative is just another name for the slope of the tangent line at a point. Then we have, let's do the general properties first. We had what I'll call the constant times a function property. I wish this one had a better name, but I can't find a name, so I just made it up. That if my function is really essentially a number times another simpler function, I'll call it the essence of the function. The number in front is just a stretching transformation of something else. Then that stretching or compression transformation is what's happening to the derivative as well. And I leave the number in front and can look at the derivative of the essence of the function. So these properties are allowing me to look at smaller pieces and then use that to build the derivative of the original function. And if I look at simple enough pieces, then they're pretty much my basic functions. One more way a function can be broken up is by looking at the sum or difference of terms. So this one is called the sum difference property, saying that if my function is made up of two simpler functions added or subtracted, then I can find the derivative of the original by just reconstructing the individual derivatives of the simpler pieces. Giving me a chance to work with derivatives, slopes, and all of those kinds of things of much more complicated functions by just piecing the derivative of the individual terms together. And then we have arguably, at this stage, the most important property, the power rule. That if my function is a basic polynomial, then the derivative is obtained by the following formula. And we had some basic functions, x squared, x cubed, x to the 4, that we had to use the limit definition on, and then we noticed a pattern, and that pattern does indeed continue. So this is what we have so far. This is what we have so far. And with that, we can do a fair bit. But I want to first extend the power rule because it actually covers more things than just polynomials. So let's leave this page, I think, since there are more properties here. And I'll say for now, n is a positive integer. For now, this power rule only covers my basic polynomials. But I have other basic functions. And there are two of them that are not polynomials. The first one is the square root function. Let's look at our other basic function, not a polynomial. Let's look at the square root function. Now, in order to first examine this function and its link between what the function looks like and what its derivative looks like, I need to use the limit definition to find that derivative. And in the case of the square root, it's not going to be the most fun you've ever had, but it's unfortunately what we have to do as we're trying to cross over getting away from the limit definition. I still have to look back at it because that's technically how we do find these derivatives. I do want to do it in general though, so that I can come up with a general rule for getting the derivative from the square root function. So that is my limit definition that we've memorized by now. So now, just like always, I use what the function is. In this case, it's the square root function. So when a plus h is the input, it's the square root of a plus h. And then the square root of a over h. Now that limit still has form 0 over 0. The denominator is obviously 0 when h is 0, and the numerator as well. So anything can happen. Can't say. So I need to simplify this. And in the case of a square root expression like this, there's a very specific way to simplify. I'm going to multiply by 1. And because it's 1, I haven't changed anything. But I'm just going to write 1 in a super fancy way. And it's still going to be 1. But I'm going to write it as a plus h square root plus root a over the same thing. So that second thing that I'm multiplying by still simplifies to 1, meaning I haven't changed the original answer in any way. But doing it this way allows me to get to a point where the form of the limit isn't going to be 0 over 0 anymore. Let me just do the denominator first. It's simply going to be h times the square root, a plus h plus a, and the numerator is more interesting. How can I simplify the numerator? Let me put brackets around this. Maybe that makes it more recognizable. What do you see? Do you see anything where I look at those two brackets? They're not random. They are connected in that they're the same, except one has a plus and one has a minus. So if I remember the difference of two squares, now we usually write a squared minus b squared. These a's aren't the same. Maybe I'll make them big A and b, so you don't get confused between the little a's. It's a plus b times a minus b. And I have two brackets that look exactly like this. The big A is square root of a plus h. The big B is square root of a. So now if I go from the brackets to the difference of two squares, it says it's the first one squared minus the second one squared. Does everyone understand why I am doing, or why I'm able to do that? The trick of multiplying with that second fraction, that's something you just remember. You see it a few times, and it only really is an issue for us when it's a square root. There's no other way to simplify that, really, and I have to. But once I have those two brackets that I need to simplify in the numerator, I recognize it as the difference of two squares. Then I can simplify this, because the square and the square root essentially cancel each other. So I have a plus h for the first one, minus a for the second one, and the denominator just hangs out. Looking a little complicated, but there's nothing I can do about that right now. Then the a, and the minus a cancel. And when they're gone, I have only an h at the top, canceling with an h at the bottom. So what I'm left with is 1 over square root of a plus h plus square root of a. What is the form of that limit? It's not 0. Over 0, I mean, because the numerator is 1 now. So it's much, much more predictable in what the limit's going to be. And I can plug in 0 for h, and I have no problem at all. I'll emphasize that we're plugging it in, but the two square roots in the bottom is now the same. It's 1 over 2 of the square root of a. So we're able to find it, and if I have the square root function in its most basic form, then the derivative is 1 over 2 times the square root of the x value in question. For example, zoom out a little. If I have a graph, if I have the square root function's graph, sideways parabola, I could look at maybe this point over here. Let's say that is a 3. And I can ask for the tangent line slope at that point. It has slope 1 over 2 root 3. And you can calculate that to however many decimals you want. I now have a formula for the derivative of the square root function in its basic form, but one step at a time. And you can find any, you can be interested in any other x value, plug it in, you're done. So what is the link here really? Let me write this below here. So this says if my function is the square root function, then I don't care about the a. The a is just a placeholder for the x value. So I can recycle the x to write the general rule like that. Whether I use an a or an x or a squiggle or whatever, it's just a placeholder for the x value. Now, many people remember this as a new formula, and there's no real harm in doing that, but this isn't really new. This square root function I can write as x to the 1/2. Which means I can write the derivative as 1 over 2 times x to the 1/2, or 1/2 in front, x to the minus 1/2. But that means, what does the power rule do again? The power rule takes the power of x in the original function, moves that number to the front, and then the new power of x is 1 less. That's exactly what we're doing here. Move the half to the front, the new power is 1 less, 1/2 minus 1. So this also fits the power rule, meaning it's not really a new formula. It's included in this. I just have to update that this power rule is actually much more powerful than just for polynomials. it's actually any, oh, I shouldn't have deleted the positive yet. Positive, let's call them rational numbers, which is what they are, including integers and fractions. So it can handle much more than just polynomials, x to the power of any fraction or little thing. For example, I'll do it over here. If I have, just as a side example, let's suppose I have f of x equals x to the power of whatever, I don't even know, random fraction, 7/3. Then the derivative is 7/3 in front, x to the 1 less, which I can simplify a little bit, x to the power of not negative. It depends on what the size of that number is, right? 7/3, well, 1 is 3/3, so 7 minus 3 is 4/3. But regardless, it's still just the power rule. Just be careful in the minusing 1 when I'm working with fractions. So, yes, you can memorize the derivative of the square root function, but there are many other functions with many other fraction powers of x. And I can't memorize them all. Luckily, they fit the power rule formula perfectly, and I don't need to memorize anything new. Any questions on that? So it's still just the power rule, doing its power rule thing. There's one more basic function that we have in our list so far that is not covered by these properties at the moment. Full screen, zoom in. And that is our one more basic function that is 1/x. This is our last one. Our basic functions will be finished then. Well, for that, one more time, we are going to need the limit definition. This one's easier than the square root. Maybe I should make an A. Some people don't like the x at this stage, though it really doesn't matter. Limit definition, I've written it down so many times now, couldn't forget it if I tried. Now I just have to use what the function is in this case, which is 1/x, and if the input is a plus h, it's 1/a plus h. 1/a for the second one over h. So now this one has a much more straightforward simplification. There's no trick involved. I simply have to put the two top fractions together, and I think we have done that before with a specific number. So it's good practice anyway. So now the common denominator for the top guys are a and a plus h. The left numerator is going to have to be a, right numerator a plus h, and all of this is still over h. But that is going to allow me, after cleanup, to pretty much be done with the 0/0 problem. Multiply the -1 in. This is h/1. Division by a fraction is multiplication by the reciprocal, so the h is sitting in the bottom. And now I see the a minus a I can get rid of. After that, instead of copying the whole thing again, I have a negative h here and an h at the bottom. The h's can cancel. So I'm left with -1 is still at the top, a times a plus h, which doesn't have a problem at all. And I can plug in 0 for h. We've seen that before. Plugging in 0 for h gives me negative 1 over a squared. And again, okay, that's our basic rational function. I could memorize that if I wanted to, but obviously there are way more other rational functions. This is just one that I start with. It's not going to be that helpful, but we do have it figured out now that if I have my 1 over x function, then the derivative using an x again is negative 1 over x squared. Great. But I can rewrite these as powers of x. Oops, let me just write the function again. This is x to the negative 1. This one is negative x to the negative 2. What did the power rule say? It said the original power of x is a number that goes in front. Negative 1 was the original power of x. Negative is in front. The new power of x is 1 less than the original, and that's exactly what I'm getting. So the power rule works again. Does everyone see the power rule working? I got 1 head nod. 2. Negative 3. No, you are the second one. Sorry, you can't be the third one as well. Power rule still works. If you don't see it, look at it long enough and you will. So I can update this again. Actually, any real number. Now, proving that it works for absolutely everything is a little bit hard for us. But we get the idea that this can keep getting extended and extended. Yeah, we have to go back to the limit definition every time. Not that bad. It does work. So any number you have there, power rule, as long as it's x to the power of something. I still need the other properties, right? Combining smaller pieces with numbers in front and so on. But it's a good first step. It can get me much further in terms of finding derivatives for functions than we think. So for the time being, we're going to be concerned with just practicing these properties and being aware of which property I use when. But ultimately, we are talking about rates of change. We are talking about slopes of tangent lines, so we don't want to forget that. But there's a lot of practice to get these rules down, these properties. So we sort of put the meaning of the derivative aside to just practice these a little bit. So if we just cover the problems, problem 5.1, choose a random number between 1 and 9. 6. 6 is the function 1 over x to the 5. Right, maybe 5 doesn't look very good. That doesn't look better, but that's going to be the 5. I'm not going to look at it this way. I recognize that it's the power rule, so I'm going to write this as a power of x and negative 5 in this case. Then I can just use the power rule. The negative 5 goes in front. The new power of x is negative 5 minus 1. And I'm done. Here is my preference when it comes to how your answer should look. I don't care. I don't care to simplify that. If you need to, you have a desire to simplify everything you see, go right ahead. I don't have that desire. If it's my final answer, I don't care how it's presented. Actually, more detail, less simplification is actually easier to mark. But if I need to use this function in a future follow-up question, then I might want to clean it up. In this case, it's my final answer, so I'm done. I think problem 5.1 is kind of simple. So here I'm just going to say, for now, what properties I'm using so that I can be extra aware of which property I use when. Because if I'm not aware of which property I'm using, I might not be using them right. I need to sort of make a point in the early questions to really be aware which of those properties am I using and when. Because as soon as I stop thinking about that, especially in the beginning, I make a mistake or I'm using a property wrong because I'm not really sure what I'm doing. So, moving on to the next one, there's just a little bit of notation adjustment to make the detailed use of the properties more obvious. So, we have our function. Let me just say this is our function. Y, f of x, use it however you want. They're interchangeable. Okay. It turns out there are three main ways to represent the derivative. Each one has their pros and cons, and depending on the situation, I'll flip back and forth between them. So, different ways to represent the derivative. They're not different, they're all the derivative, just different looking. First one, the prime notation. We've seen it. Its pro is that it's simple. I just use the same name as the function and put a little mark there. Great. The other one is using the y, and there will come a time when this one is beneficial, though you might not see it right now. Little d with a y and a little d with an x. That space is just random. They're connected. They're one thing. And we say dy dx. I call it the little d notation. It means exactly the same thing. And this sort of comes from the fact that the derivative is really a slope. This comes from the slope being the change in y over the change in x. And the short way of representing change mathematically is delta y over delta x. But they couldn't use the delta because it's not quite the same as the slope of the secant line. So they changed it to a d because delta. So it's not random, it comes from the slope concept. And then there's a third one, which I will use in the next problem. I call it the big D notation. D for derivative. In the bottom I say what my variable is, and then in square brackets I just write the function. I don't know the detail of the function in this case, but that's where it would go. And that big D notation just helps me lay things out in a lot of detail, which is only something I want to do in the beginning. But I feel it makes it as clear as possible between these three. Different ways, write the same thing. We're going to use the little d notation sometimes. We have already used the prime notation. I'm going to use the big D notation next. It's all the same thing. So don't look at those and think, oh no, it's something else. This is weird. It's all the same thing. Like you have your first name, maybe you have a middle name, maybe you have a nickname. It's all you. It's the same thing. All right. Problem. Any questions on this? Maybe it takes some getting used to. Yes.
Is there a reason why you would use the different notations?
Yeah, it's going to be a little more confusing when I want to really show one property used at a time. It's going to be a little more confusing and difficult to write with the prime notation. And the benefit of the big D notation is I don't have to name pieces of the function. Like here, I name it G and H. I don't have to rename anything. I can just use the x's and everything. So the benefit of the big D notation is if I want to refer to pieces of the function, I don't have to rename them, which is just unnecessary. But, I mean, you can write it in any notation you want because it all means the same thing. So 5.2, I think we've done the first one. So let's go with number 4 maybe. That's interesting enough. So now, I'll write my function here, sure. Negative 4x to the power of 5 plus 3x squared minus 5 over x squared. Okay. So I'm now going to write this in excruciating detail so that we are aware of every property that we're using and when. Of course, once we get comfortable with it, we don't have to write it in this much detail. And if the question doesn't ask me to do this much detail, you don't have to. Just our first example, because I've seen people not really be aware of the properties and then using them wrong. So this is my attempt to fix that. So I am just swapping names. I'm not doing anything. It's the same thing. Prime notation, big D notation, same thing. What is the first property that I'm going to use? What's the first property? I can only, now I'm going to sort of really pull this apart. So I can only use one property at a time. What is the first one that I should use, would you say? We only have a few, right? We don't have that many. What are the options? The options are constant property, constant times a function, sum difference, power rule. 4 options. Which one is first? Which one is first? I have to isolate these terms first before I can use anything else. So the sum difference property is first. I'll write it at the end. I'm just not sure how much space I'll have. So it's going to be the derivative of the first term plus the derivative of the next term. The sum difference property doesn't say much, but it is a property. And without it, I am kind of stuck. So sum difference property. See, so the big D notation just helps me not name anything, which is a little bit more convenient. I can go directly to my actual terms. When you can't write stuff like negative 4x to the 5 prime. You can't do that. That's not allowed. I have to name the function before I can use the prime notation. So it's not convenient in this case. Doesn't matter, they all mean the same thing. Sum difference property. One property at a time. Now, I could maybe update this bottom one, this last one, sorry, because I don't like the x in the bottom. I could write that as 5x to the negative 2. Now it looks the same as the others. For all of them, which property comes next? You have the list in front of you. There are only 3 options left. Which one is the very next one? I know you want to say the power rule because it's so powerful, but the power rule requires that I have something like this. And it's not ready. It's not ready for that. I have numbers in front, which means I need to address those numbers first before I can isolate the power of x. Let me backtrack on that. So it's the constant times the function property that allows me to write this. And in the second case, the 3 goes in front. Oops, no, not equal, minus. And then the 5 goes in front. Constant times a function property. It should have a nicer name. And the fact that it doesn't have an impressive name makes me feel that it's not important. But without it, I actually can't get to the power rule. They all work together to isolate the essence of the function in each term. Now it's power rule time. Leave the negative 4 in front. The power rule says that 5 goes in front as well, x to the 4. There's a 3 in front in the second term. 2 goes to the front as well, x to the 1. I'll write the 1 there, though you don't have to. I have a 5 in front. Now a negative 2 goes in front as well, and it's x to the negative 3. As a note, as a side note, while I'm thinking of it, many people are afraid of brackets, though I don't know why. Write something like this. Can you see the dot? How about now? If I don't clearly see the dot, that's not correct. Because that now means blah, 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 minus 5 minus 2x to the negative 3, and that's not right. If you're not using brackets, make it extremely clear that you are multiplying. Or just accept the niceness of the brackets. Then there's no confusion. I'm saying this because I see people every time. I'll put a dot there. That dot is barely visible. Now I don't know. I don't know. It's awkward. Which way do I go? You don't want me to have any doubt. Power rule is used. Do I go any further? Do I simplify? There's no wrong answer. You decide for yourself. If you have strong feelings towards simplification, and I know previous courses you were in probably made a whole big deal about simplification, I am not going to. I don't care. That's my final answer. It's perfect. It's perfect the way it is. But you are welcome to put the 4 and the 5 together and make it 20. Doesn't change. I don't care. It's fine. I'm not discriminating between that and not perfectly simplified answers. Still the same answer. In fact, the detail makes it easier for me to mark because I can see that you knew what you were doing. If you simplify it too fast, then it's sometimes hard to know if you've done everything correctly. Questions? Thoughts? Does it make sense? There's only 4 properties. It's not that bad. But be aware of what you're using when. And every time I do this, every time I say this, every time there are people thinking, I'll just do it. Don't worry about it. And then they're not aware about every single property. Eventually things get more complicated and they do something wrong because they don't really know what they're doing. You have to be aware of what I'm doing, even the little properties. All right, let's make our own example, or maybe it is somewhere. Let's make my own in the last few minutes. Ooh, not enough space. There are more to practice, and yes, there are more properties, but this is a good starting point for now. Problem 5.1 and 5.2. One step at a time. Go figure. There we go. Let's just make another example. F of x. Let's say x squared minus 3 root x plus 1 all over, let's make it the cube root of x. Why not? Why not? So there I see it's even worse than a rational function. it's not even polynomials, but it has this fraction look to it. And I don't have any properties to handle fractions just yet. These are my properties. I have 4 of them. Can I still do it? Can I? I just have to rewrite this and make it look nice. So before I worry about the derivative, I'm going to sort of separate these over the same denominator. Because it is the same denominator. I won't simplify too much right now, just so everyone can see what we're doing. And I do this because right now I don't have a property to handle the function in its current form. But I can still do it. Now, I also know that these are still fractions. I can handle single powers of x with numbers around them. So if I notice that the cube root of x is x to the 1/3, I can simplify this to x squared minus 1/3. I just don't want to show too little, so I'm going to make it clear what we're doing here. I have my 3. I have x to the 1/2 at the top, minus another 1/3 as I'm moving the bottom one up, and then I have x to the negative 1/3 because there wasn't much at the top. Clean that up. X to the power of what in the first term? Oh, fractions. You realize your calculator has fraction options as well. That little ABC button? 5/3. And then minus 3x to the 1/6. However you do it, make sure you can do it. And x to the negative 1/3. So now there was a point to me simplifying the top fraction function, because my properties were kind of limited at this stage. Yeah, we're going to expand on them, but one thing at a time. Now I'm ready, and I can say my derivative is this function that I'm trying to find, and because I haven't done a lot of examples yet, I am going to remind myself which properties I'm using at every stage. First property that allows me to look at one term at a time is the sum difference property. So though you may be tempted to merge some properties and do them at the same time, I don't want to do that right now. Sum difference property. If I go too fast and I'm not aware in these early examples, it's going to get sloppy later. Now, I'll leave these guys as is because the middle one is not ready for the power rule just yet. I need that 3. I need to address the 3 in front first. And there is a property that does that. So just to keep things all together, I'm using the constant times a function property. Get that 3 out of there. Then they're all ready for the power rule. And I just have to keep track of these annoying little fractions. The 5/3 goes in front. The new power of x is 2/3. The minus 3 was already in front. See my nice big dot or brackets. 1/6 goes in front. X to the negative 5/6. One less. Plus, just to emphasize, yes, I could write minus 1/3. But that's more of a simplification. I don't need to worry about. The new power of x is negative 4 over 3. And this was the power rule. Simplify that, don't simplify that. It's my final answer, I could not care less. But be aware of which property does what and when. And very soon we won't be doing this. We'll do them much faster and put basic properties together at the same time. But we need to get comfortable that in case things get complicated, I need to know what I'm doing at every stage. So do this for a few of them and decide when you're comfortable to do it in a shorter way.
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.